Hello, my name's Alex, and this presentation will be on our recent publication in the Journal of Magnetic Resonance Imaging, which comes from a collaboration between the Biomedia Group at the Department of Engineering Science of the University of Oxford and Perspectum. Pancreatic diseases like steatosis, fibroinflammation, and cancer are spatially inhomogeneous. Quantitative MRI imaging biomarkers like proton density fat fraction and T1 have shown potential for early detection and monitoring of steatosis and chronic pancreatitis. Some studies using quantitative MRI have reported clinically important differences between pancreatic subsegments, namely pancreatic head, body, and tail, as illustrated in the figure. The analysis of quantitative MRI images has traditionally used manual placement of regions of interest, ROIs, particularly a 3 ROI strategy targeting pancreatic head, body, and tail, as illustrated. Recent automated analyses have implemented whole organ segmentation, which provides a global measurement, but fails to describe spatial heterogeneity or quantitative differences between regions. We believe that pancreas subsegmentation can help bridge the gap between currently available technology and standard clinical assessment. No validated methods have been reported for pancreas subsegmentation. So the purpose of this work was to develop and validate an automated method for pancreas, head, body, and tail segmentation in abdominal MRI. We show initial application of the method in regional assessment of pancreatic disease. We used 150 healthy subjects from the UK Biobank imaging study, 100 for method development and 50 for validation. Manual whole organ delineation was performed on all 150 subjects. A separate set of subjects from UK Biobank was included, containing subjects with self-reported type 2 diabetes and gender and age matched nondiabetics. The subjects underwent abdominal MRI with Siemens 1.5 Tesla scanner, including a 3-dimensional 2-point Dixon scan that was used for segmentation, and a 2D axial multi-echo gradient echo scan for proton density fat fraction quantification. The method consists of an offline template creation step in which average representation of the pancreas across the population was built using group-wise registration. Parts were then manually annotated to yield the pancreas parts template. For a new subject to be segmented, the method first registers the new subject's whole segmentation to the parts template. In step 2, we use the inverse transformation to warp the parts template to the subject. Finally, we perform label propagation from the warped parts template to the subject segmentation, obtaining a part segmentation for that subject. For validation, 4 raters with a wide range of experience annotated the validation set. 10 out of the 50 subjects were included twice for intra-rater variability assessment. The validation set was also subsegmented using our automated method, and also with an implementation of the k-means method from previous work. Inter-rater variability was used as our benchmark for the automated results. Dice overlap and the 95th percentile Hausdorff distance were reported as segmentation performance metrics. In order to quantify fat from subjects, we intersected the 3-dimensional parts segmentation with the PDFF maps acquired from the separate gradient echo scan, using the reference coordinate system from DICOM. This resulted in a 2-dimensional part segmentation mask, as shown in the figure. The median fat fraction was reported for each segment. Parts quantification was performed for the validation set subjects and also for the matched diabetic cohorts. Here are the 3-dimensional renderings of part segmentations from the first 10 validation set subjects. Segmentations from manual raters and from the automated methods are shown. Our group-wise registration method showed excellent agreement with manual raters in all three pancreatic segments, head, body, and tail. Conversely, the previously reported k-means method showed differences with manual raters in the head and body segments. Our group-wise registration method showed similar PDFF quantification when compared to manual results and also to the previously reported k-means method. For our exploratory study in diabetics, we found a significant difference in pancreatic fat between type 2 diabetics and the low BMI non-diabetics cohort when comparing head, body, and tail. We found a significant difference in pancreatic fat between type 2 diabetics and the high BMI non-diabetic cohort when comparing body PDFF. When comparing differences between pancreatic parts within the same cohort, a similar pattern was observed for all subject groups. The differences between head and body PDFF, as well as the differences between head and tail PDFF, were significant, whereas the body versus tail PDFF differences were not significant. To summarize, we successfully validated a method for pancreas head, body, tail segmentation against manual annotations. The method shows potential for automated measurement of pancreas subvolumes as novel imaging biomarkers. The derived PDFF quantification from our method was also comparable to manual results. Furthermore, the regional differences observed in pancreatic fat between diabetics and matched high BMI non-diabetics demonstrates the importance of subsegmentation beyond global measurements of pancreatic MRI biomarkers. In conclusion, we demonstrate automated pancreas subsegmentation and regional quantification of pancreas MRI biomarkers. Our method enables segmental characterization of heterogeneous pancreatic disease. Whilst we have studied pancreatic fat in this work, note the method is readily suited for the assessment of other imaging biomarkers, such as T1, as shown. Thank you to our collaborators, and please find out more in our recent publication in the Journal of Magnetic Resonance Imaging. Thank you for your attention, and see you next time.